So hello everyone. In this video, we are going to discuss about synchronization primitives. So we are going to primarily discuss some challenges in concurrency, and particularly these are the race na conditions. And we will also discuss the critical section, mutual exclusion, and how to enforce it. And lastly, the readers, writers na problem. So let us start by motivating parallelism. Okay, you can see here that as technology advances, there is also an increase in the number of transistors. So you can see that starting, let's say, from 386 to Pentium until dual core Itanium 2 until the more recent models that we have, there is substantial increase in the number of transistors. Okay, so although we can see here an increase in the clock speed, the power draw, and the perf or clock, then we can see that there are no longer that much increase starting from 2000 until starting from 2000. Okay, so what are the impact or the implications of CPU in evolution? With increasing transistor count or the clock speed, then we have also an increased number of tasks that can be executed concurrently. Okay. However, as mentioned, you have seen that the clock speed increases have essentially stopped in the past few years. Instead, we saw that the more transistors that were included, then there are also more na CPU cores. And with more CPU cores, then there is also an increased opportunity for parallelism. Okay, and what is the difference again between concurrency and parallelism? So suppose we have this model, we have four processes. This is how they are executed concurrently in a single core na system. So we can see that we have only a single core. And what happens here is it seems to the user that these processes are run in parallel, but in fact, there is actually an interleaving, okay? Or the processes are switching on the use on the CPU. Okay, let's say for P1 uses the CPU and then it gets preempted and then P2 can use it again, can use it next, and then it gets preempted, then P3 can use it next, and so on and so forth. Well, the parallel execution in a dual core na system, so we can see here the emphasis on the dual core. Okay, so we have two cores and these processes that we have can run in parallel in these two na cores. Okay, so in a multi-programming environment, the processes executing concurrently are either competing or cooperating. And what are the responsibilities of the OS? So if there are competing na processes, so the job of the OS is to carefully allocate the resources and to properly isolate the processes from each other. So we make sure that each of these independent na processes will be able to use the CPU as they need without efficiently and without much na waiting, right? And for cooperating na processes, in here, the job of the OS is to allow some processes to interact with each other. So what's the difference between competing and the cooperating? So for competing na processes, these are independent na processes, right? So that's why OS needs to properly isolate the processes from each other. While on the cooperating processes, these processes are sharing on some resources, and the processes then are allowed to interact with each other, right? So what would be the job of the OS? To have some protocols to allow these processes to share these resources. Okay, again, for these competing processes, these processes compete for devices and other resources. So in this case, The processes are independent and are unaware of one another. Okay. So for example, the independent processes that are running on a computer. So what would be the properties? So yeah, and the potential na problems. Yeah, it is deterministic. So one process may be started or stopped without side effects. Okay? Because the processes are competing, and the tendency is one process might use a certain resource that is actually should be assigned for another process, let's say. And so then the starting or stopping randomly, let's say. And it is also reproducible, and which can proceed at an arbitrary rate. What about for the cooperating processes? So in contrast to the competing processes, cooperating processes are aware of each other, and they do this by communicating or by sharing resources. And the problem is this may affect the execution of each other. So, for example, the transaction processes in railways or airline or stocks. So, let's say dito sa airline, they are using, or let's say dito sa railways, there should be some schedules, right? Kasi isa lang naman yung railway. So, ano yung schedule ng mga trains? Or let's say, ano yung um, such that hindi magbubungguan yung mga trains. Okay, let's say yung sa airline. So ano yung mga magiging schedule ng mga plane kasi limited lang naman yung mga planes natin and all. So then for the properties of these cooperating na processes, so they share resources or information, but it is non-deterministic and maybe irreproducible, and there will also be some race conditions that will happen. So race conditions, they are racing on using that certain na resources. So we will see later on with some examples what this race condition is. So why cooperation? So with cooperating na processes, so they can share some resources. And for example, one that could check the account. So you can think of it like in in a bank. So there will be many tellers who will do different jobs. Okay, and us as clients, so we can queue on this several na um, tellers. Okay, and then we can also have a speed up with cooperating na processes because they are sharing resources. So we can read the next block while processing the current one. So here's the part where we are doing it in parallel. So we can already start reading one process while executing the other one. And we can divide jobs into smaller pieces and execute them concurrently. And there is also the modularity, or we can construct systems in a modular fashion. Okay. And what about for competition for resources? So, and because with competition for resources, there are conflicting na demands. So there is a demand for the use of I/O devices, or the memory, or the process time, right? And if there are some processes that are blocked, then the tendency is the system or the total time will be slow, or this process will never get access at all. And what are some problems that we could encounter here is that there is a mutual exclusion, or mutual exclusion, and then on how to enforce this mutual exclusion. So we have this example. So let's say we have this certain na memory that contains some data. Okay. And the process A changing the data in a memory location, while the process B is trying to read the data from the same na memory location. So, if these two processes are executed concurrently, so there might be some problems. Okay, since they are um, acting on the same or acting on the same resource or memory. So there is a high probability that the data read by the second process will be erroneous. Okay, so for example, process B is trying to read the data, but then process A has already replaced it with a different na data. Okay, so again, because of that, there is a high probability that the data read by this second process will be erroneous. So let's say we have this example. We have an array A with three elements, 3, 4, and 5. And we have these two processes. So process one is that we are adding A of 0 and A of 1. That means that we are adding these first two elements and storing it in A of 1. So in other words, we are changing the value of A of 1 with the sum of A of 0 and A of 1. And we also have a process 2 that has this task. So A of 2 is equal to A of 1 and A of 2. In this case, process 2 is adding the last two na elements, 4 and 5, and storing that into the A of 2. Okay, so what would be the value or the final na value of A of 3? So it would be 3, and then what would be the last two na elements? So this is a statement level na execution interleaving, or what essentially what it means is these two processes are run concurrently. So let's say this process 1 will run first, followed by the process 2, or that this process 2 will run first, followed by the process 1. So it is non-deterministic depending on what process will be executed by the CPU first. Okay, so assuming that the process 1 updates first, so in this case, the A of 1 will be 7. Okay, since A of 0 is 3 and A of 1 is 4. And then there will be a context switching and process 2 will run now. So in this case, the value of A of 2 will be 12 because A of 1 is now 7 plus A of 2, which is 5. So then the value or the elements of A of 3 will be 3, 7, and then 12. Right? So what happens if the process 2 updates first or is run by the CPU first? So in this case, the A of 2 will be 9. So in-update niya muna sa A of 2. So dito is in-update muna sa A of 1 followed by A of 2. But in this case, A of 2 is updated first. So the result of this will be A of 2 equals 9 since A of 1 is 4 and A of 2 is 5. So 4 and 5 will be 9. Context switch and the process 1 will run now. So in this case, A of 1 is equal to 7. So A of 0 and A of 1, that is 3 plus 4, and that results to 7. So the final value or elements pala of the array is 3 followed by A of 1, which is 7, and A of 2, which is 9. So we can see that the results are non-deterministic. Okay, because when we go back here, if process 1 updates first, the content of the array will be 3, 7, 12. But in this case, if process 2 runs first, the content of the array will be 3, 7, and 9. Okay, so which is which? So that's why that there is a need for synchronization. Okay, let's have another process, or let's have another example. So we have int na count, and suppose we have two processes that are sharing on the same na variable. And the process 1 is incrementing the count while the process 2 is decrementing the count. So what would be the value of the count? So it depends on which process will be run first. Okay, again, the results are non-deterministic and there is a need for synchronization. Now, another example here, consider a simple banking application. So it is a multi-threaded na centralized na architecture, and all the deposits and withdrawals are sent to the central na server. Suppose that two people have access to same na accounts, right? So this will be or they both try to deposit in the same account. So that would be balance equals balance plus sum, right? So the sum of this uh, the current balance that we have plus the deposit or the sum, and then that will be stored to the balance of variable. So in other words, we are updating this variable. Okay, so again, what happens if two people try to deposit money into the same account at the same time? So this is, let's say, the pseudocode um, for the balance equals balance plus sum. So essentially, on on the machine level, so let's say we are using assembly. So we move EAX balance to EAX, and then we move sum to EBX, and then we are going to add EAX and then EBX, and then store the value in the EAX, right? And move the value of EAX to balance. So again, there are two people who tried to update to deposit, right? So initially the balance is 0. Okay. And let's say person one or in thread one, the person tried to deposit $50. Okay. So balance to EAX and sum to um, EBX, right? So in this point, they are sharing the same variable EAX, and at this point, AX is 0 pa lang siya. Okay, and then context switch, the thread 2 wants to deposit $100, and it will perform also this the same na code. So move AX balance and move EBX na balance, and then we add EBX to EAX. So that means that the balance, which is 0 plus 100 na 100 na sum, right? So now the EAX is now $100, and that AX move balance to AX. So kumbaga, this balance will now be equal to EAX, which is $100. And is another context na switch. So this thread 1 will continue its execution. And we go back, we add um, EAX and EBX. So in this case, they have separate na registers, diba? So this will be EAX, which is equal to $50. Okay. Since we have a sum which is equal to 50 plus 0, and then we move EAX to balance. Okay. We have a separate method. That's why we have not taken into account the value of the balance here. Okay. So in this case, the balance here is 0 plus the sum, which is 50. Okay, that's why the value of the balance or EAX is 50, and so the balance will be 50. So the result is erroneous. So the correct answer is supposed to be 100 na 50, but then these two threads have access at the same time and have caused erroneous na results. Okay, so the previous example shows a race na condition. What happens is two threads race to execute code and update the shared dependent na data. In that example, it was the variable EAX. Okay, and the errors emerge based on the ordering of applications, as well as the scheduling of threads. Thus, the errors are non-deterministic.